Right. So, um, just a small recap. As I told you that we determined the whole current density at the edge of the depletion region on the N side with this relationship, and then the electron current density at the edge of the depletion region on the P side with the help of this relationship. And then if you add these two together, you get the total current density. And this is called the prefactor for this equation. We call it, the prefactor is called the reverse saturation current density, represented with JS. Then you can replace some of the values in this equation, like for example np naught with ni squared divided by na, pn naught with ni squared divided by nd, and the diffusion length with the square root of diffusion coefficient times recombination lifetime. So this is a more effective way of calculating the reverse saturation current density. And reverse saturation current density is the current density under reverse bias voltage because of the diffusion of minority carriers in these regions. So the total current density is equal to the reverse saturation current density times the exponential factor -1. Here is an example, and in this example we are asked to calculate the ideal reverse saturation current density in a silicon PN junction at 300 Kelvin, which is room temperature. The parameters for the silicon PN junction are also given: acceptor doping, donor doping, Ni, which would be the same for silicon at room temperature. Then the diffusion coefficient for electrons, diffusion coefficient for holes, its unit is centimeter square per second. The recombination lifetime for holes and the recombination lifetime for electrons. It's assumed as 5 10 to the power of -6 seconds, or 0.5 microseconds. And similarly, the relative dielectric constant is also given, relative permittivity. So the ideal reverse saturation current density, as I told you, there are two equations, but this one is more effective because you have all the values given for this equation. Just replace all the values into this equation and you get a value of 4.16 into 10 to the power -11 ampere per centimeter square. Remember, the unit is ampere per centimeter square because we are talking about current density, not current. How do you calculate the current? Assume if the area of the diode is 10 to the power of -4 centimeter square, then the reverse saturation current would be the product of the saturation current density times the area of the diode. So, which is 4.15 10 to the power of -15 amps. It's in femtoamps. The reverse saturation current density is really small, ideally, but in reality there are so many non-idealities. Shockley red hole recombination, OJ recombination, direct band-to-band recombination, and because of these factors, the reverse saturation current density is not the same. It's much higher than this value. Okay, now we got another example, and in this example we are asked to design a PN junction diode to produce a particular electron and hole current density. So consider a silicon PN junction diode at room temperature. The electron current density is given, the hole current density is given, the applied voltage is given, the remaining semiconductor parameters are given in 8.2. And design the PN junction diode basically here means to suggest the acceptor and the donor dopings for this PN junction diode for these current densities, and the remaining semiconductor parameters are given in 8.2. So use all the parameters of 8.2 except for the acceptor and donor doping. You have to calculate these. So we have the equation for electron current density, as you can see in this slide over here. And then replace NP naught with Ni squared divided by Na, and then Ln with its value, and you got the equation in this form. Ln is equal to Dn times Tn. Anyhow, so from this equation you already know all the remaining parameters. The current density for electrons is given 20 amps per centimeter square. Everything else is given. Charge on electron, by the way, is 1.6 10 to the power minus 19 coulomb. You should know this number. The applied voltage is 0.65 which is over here, and A is unknown. Reorder this equation and you get the value for Na. Excuse me. And then the whole current density is given by another equation, which is once again given in the previous slides, is equal to charge on electrons, everything else, and D is unknown. The whole current density is also given. So just by reordering this equation, you can also determine the value of Nd, or the donor concentration. Now, as I already told you that the total current density through the PN junction diode is a constant. But how does it work? What kind of individual current densities do we have in the individual regions? So for example, let us start from the electron current density. In the N region, electrons are the majority carrier concentrations. So majority carrier concentrations, and then they're diffused towards the depletion region, remain constant inside the depletion region, and then diffuse further into the p-type region. But during this diffusion process, they recombine with the majority carrier holes in the p region, and their number gets reduced with the passage of time over distance in the p region as well. Similarly, holes are the majority carriers in the p region. They diffuse through the depletion region into the n region, and their carrier concentration exponentially decreases. Now the total current density in the n region is the sum of the majority carrier electron current density plus minority carrier hole current density, and you add these points together everywhere. It gives you a constant value. Similarly, in the p region, the total current density is the sum of the majority carrier hole current density plus the minority carrier electron current density, and you add them together, you get a constant value. So throughout the PN junction, the total current density would always be constant. It will have the same value. And then in the previous slide, we calculated JPF over here, JPF xn and Jn of minus xp, which is just a single point at the edge of the depletion region on the n side and at the edge of the depletion region on the p side. But how about the current density of holes as a function of distance and the current density of electrons as a function of distance? So as a function of distance, anywhere in the p region and also in the n region, you got this relationship over here, which include all the previous values, but there is an additional exponential e to the power of xn minus x. Xn is the edge of the depletion region, this point, minus x is any point in this region divided by the diffusion length of holes. Similarly, for the electron current density in the p region, we have the previous values, parameters, and then an additional exponential e to the power of xp plus x. Xp is this point, the edge of the depletion region on the p side, excuse me, plus x, which is any point in this region, divided by the diffusion length of electrons in the p region. And then the total current density is the sum of the individual electron and hole current densities. So here is another example. Calculate the electric field in a neutral region of a silicon diode to produce a given majority carrier drift current density. Consider silicon p-n junction. T is equal to 300 Kelvin. Parameters are given in example 8.2. Applied voltage is also given. So in example 8.2, we calculated Js. Look at example 8.2 once again. Js is already calculated. And in order to calculate the current density would be equal to Js times e to the power of EV. EV applied voltage is 0.65 given as well, divided by KT is 0.0259 electron volts minus 1. So the total current density is 3.295 ampere per centimeter square. And we have to determine the electric field. So just to confirm, I lost the connection on one of the side computers. Are you still able to hear me?
Yes, sir.
All right.
Yes, sir.
Okay, nice. So we are still good. Okay, good to know. If for some reason you are not able to hear me, just send me a text on WhatsApp, okay?
Okay, sir.
All right. So I got connection on the side computer once again as well. So okay, we found out the total current density and we have to calculate the electric field. So as I already told you, the total current density is constant throughout the p-n junction. So if we calculated the total current density, we can and then assume any point, it would be the same. So just assume that the total current density at this point, it's going to be the same, 3.295 amps per centimeter square. Okay, over here 3.295 amps per centimeter square. Okay, so now I got a question for you. The total current density at this point would be the sum of the electron current density plus hole current density. But what do you think about the hole current density at this point? It's negligible, right? You can see it over here. It's almost zero. So almost all the contribution comes from electron current density over here for the total current density. So you can say the total current density here is equal to the electron current density. That is 1 point. J is equal to Jn. And then which is further equal to, in the neutral region, here we are talking about the neutral region. Now we are staying away from the diffusion happens in this region over here. But we are away from the diffusion region. So away from the diffusion region, the current would flow because of drift. And the equation for drift is this one. Charge on electron times mobility times the donor concentration times the electric field. The donor, because electrons are the majority carriers, times the electric field. So just reorder it for the electric field. Replace all the other values. Mobility is not given over here, but generally the mobility of electrons for silicon is 1350 centimeter square per volt second. Per volt second. Similarly, the mobility of holes for silicon, I think, is 480. It's close to 500. I forgot the exact value, but it's close to 500 centimeter square per volt second. But replace all the values and the electric field is 1.525 volt per centimeter. Temperature effects. So far we talked about the ideal IV characteristics of a p-n diode under thermal equilibrium. What happens? How do you relate it to temperature? Is it a function of temperature as well? So to find out that, let us go into the details of the equation. J is equal to Js e to the power of EVA divided by KT minus 1. So you already see this KT value over here. It's a function of temperature and it's a function of voltage as well, but the thermal energy does not really change a lot, but it's a function of voltage. You can see that clearly. Then how about Js? Js is further equal to this, and each one of np naught is equal to ni squared divided by na, pn naught is equal to ni squared divided by nd, and I, so Js is a function of ni square, and I is further a function of the band gap of the semiconductor divided by 2 kT, and it's also a function of temperature. So J is a function of temperature and Js is also a function of temperature. So basically you can see there are two factors which are functions of temperature. So if you increase the temperature, the current density for the PN junction diode would also increase. And for a silicon PN junction, the ideal reverse saturation current density would increase by a factor of 4 for every 10 degree rise in temperature. So assume that the reverse saturation current density is 5 picoamperes at 25 degrees C. So what would be the current density at 35 degrees C? If it is 5 picoamps per centimeter square, or instead of current density we can talk about current as well, but anyhow, if it is 5 picoamps per centimeter square at 25 degrees C, what would be the current density at 35 degrees C? It's a 10 degree rise in temperature, right? So the current would increase by how many times? 4 times. Means 4 into 5, 20 picoamps per centimeter square. Yeah, but I mean the conclusive point over here is that the conclusion over here is that the current density is also a function of temperature. Example 8.5. Determine the change in forward bias voltage on a PN junction with a change in temperature to maintain a constant diode current. So consider a silicon PN junction initially at 0.6 volts at room temperature, and then the temperature increases to 310 Kelvin. Calculate the change in forward bias voltage required to maintain a constant current through the junction. So we want to change first we have an initial voltage and in a particular temperature, and we have a particular current density value for that, and then we want to increase the temperature and if you increase the temperature and we want to decrease the voltage such that the current density remains the same, and we have to find the second value of the voltage for which the current density would be the same. We have this relationship. It's a function of voltage and it's a function of temperature and a band gap as well, but we know the band gap of silicon. We are not changing the band gap. So assume two equations. J1 is equal to the same equation, and at T1 and also applied voltage VA1. T1 is 300 Kelvin and VA1 is 0.6 volts. And then J2, which is equal to J1, we want to keep the current density constant, is equal to, it's the same equation, but here we got T2 and VA2. T2 we already know, it's 310 Kelvin. VA2 we don't know, this is the only unknown variable in this equation. And J2 is equal to J1, which means this would be equal to 1. So replace all the values in this equation and then solve it further. You can easily solve it and you get to this equation over here, and then the band gap of silicon at room temperature is approximately 1.12 electron volts. VA1 is given, T1 is given, T2 is given. Replace all the values, reorder the equation, and you get the value for VA2. So in order to keep constant current density, you got to decrease the voltage from 0.6 to 0.58 to 7 volts. Anyhow, that concludes the ideal current voltage characteristics for a PN junction diodes, for a normal PN junction diode. But now I want to talk about a particular PN junction diode, and that diode is called the tunnel diode. But before going into the details of the tunnel diode, I want to go back to the energy band diagrams, and I want to show you something. By the way, it's flu season, and I caught flu as well. I hope you guys stay away from flu. But I've seen a lot of people around me catching flu as well. So let's look at this energy band diagram. Here we see that for N-type semiconductor, this Fermi energy level is close to the conduction band. Similarly, for the P-type semiconductor, this Fermi energy level is close to the valence band. But try to remember this point, that here the Fermi energy level is close to the conduction band, but it's below the conduction band. And below the conduction band signifies that it's not heavily doped. Its doping might be in the range of 10 to the power of 17, 10 to the power of 18, or 10 to the power of 10 to the power of 19 per centimeter cube. Similarly, over here, the Fermi level is close to the valence band, whereas above the valence band, which once again signifies that its doping would be below 10 to the power of 19 per centimeter cube. But if you dope it heavily, this Fermi level gets further closer and closer and closer to the conduction band. And if you increase this doping to above 10 to the power of 20, for example, then this Fermi level would even cross the conduction band energy level, and then the Fermi energy level would be above the conduction band. Similarly, if you keep increasing the hole concentration over here, this Fermi level gets closer and closer and closer to the valence band, and there comes a point where it crosses the valence band and goes below the valence band. And when the Fermi level crosses the conduction band or the valence band, we call it degenerately doped semiconductor. In normal cases, when it's inside the band gap, we call it non-degenerately doped. But when it crosses the conduction band or valence band, we call it degenerately doped, or very heavily doped semiconductor. So now let's go to the tunnel diode once again. In the tunnel diode, it's a PN junction once again, but in this case both the N region and the P region, they are degenerately doped. As you can see that the Fermi level have now crossed the valence band for the P region. Now in this case we have the P region on the right and the N region on the left, so don't get confused with the order of the P and N region, but we have the P region on this side and N region on this side. So now the Fermi level has crossed the valence band. Similarly, the Fermi level has crossed the conduction band. So these are degenerately or heavily doped, or doping of the order of like 10 to the power of 20 or even higher per centimeter cube. Now the IV characteristics of a tunnel diode are actually different as compared to the normal diode, especially at low forward biasing, and I'm going to show you how. Before that, we discussed it in the previous lecture that the depletion width is inversely proportional to the doping of the semiconductor. If you increase the doping, the depletion width would decrease. So since this is a heavily doped material, both the P region and N regions are heavily doped, So the depletion region would be really narrow. The space charge region would be, width would be narrow. It's like less than 10 nanometers. Okay. Now let us talk about biasing of the tunnel diode. So under zero bias, once again, the Fermi energy level is going to be constant even for the tunnel diode. Okay, what happens if you increase the forward biasing, or if you apply positive potential to the P side? As I already told you, once again, if you apply positive potential to the P side, all the energy levels on the P side would be dragged down. So you apply positive potential, the Fermi levels are dragged down, and now the quasi-Fermi level on the P side is slightly lower as compared to the quasi-Fermi level on the N side. But now we got a significant, we got a scenario. In this scenario, we have empty states over here on the P side, which are directly opposite to a bunch of electrons on the N side. So it's like water level. If the water level is the same, water is not going to flow from one side to the other side, right? But now we have brought down one side, so now the water level is not the same. So water can easily flow from one side to the other side. And why does it flow? Because this is a really thin region. So electrons can tunnel through this thin region and move into the other side. Similarly, if you further increase the voltage, this P side, the energy levels on the P side would be further brought down, and now you have the Fermi levels aligned with the valence energy level and the conduction energy level for the respective regions. So now you got maximum empty states directly opposite to a sea of electrons on the N side. So maximum number of carriers would flow from the N side to the, or tunnel from the N side through the depletion region to the P side. So the current would be maximum in this scenario. What happens if you further increase the voltage? If you further increase the voltage, now the number of states, empty states, which are directly opposite to free electrons have reduced. Now this region has reduced, so the current would start reducing. Further increase the voltage. Now you don't have empty states directly opposite, okay? But now we see that electrons, instead of tunneling through, this barrier becomes smaller. So the diffusion mechanism dominates once again over here. It's easy for electrons to cross over to the P region and for holes to cross over to the N region through diffusion. So now the current would start increasing once again, but now this time because of the diffusion mechanism. So for the normal diode, its IV characteristic looks like this exponential rise. But for the tunnel diode, initially there is an increase, and then there is a decrease, and then once again there is an increase in current under forward bias voltage. And this actually, if you want to determine if you really got a tunnel diode, you need to see this increase in current and then a decrease in current. One of my colleagues was actually working on gallium nitride based tunnel diodes, and he was able to find out this kind of behavior for the tunnel diodes. And if the current is increasing with voltage, it means it has positive resistance. But if the voltage is increasing and the current is decreasing, it's called negative differential resistance. So negative differential resistance is once again a key sign of the tunnel diode, and it's this region over here can be used for oscillators. So it's an important mechanism. What happens under reverse bias? Under reverse bias, you apply positive potential to the N side. So the energy levels on this side would be brought down. Now, once again, analogous to the example of water flow, water can flow easily from this side to that side. So electrons can tunnel through from the P region to empty states in the N region. And then this gap is going to increase and increase. So with increase in voltage under reverse bias, this current would keep increasing. That concludes the lecture part. Now I got more homework problems. This is your assignment number 2. I already shared Neiman's book with you, and I'm going to upload it on the Google Classroom as well. So this time you got to solve these problems. I've assigned less number of problems to you this time, uh, and it's still a considerable number, but I want you to practice, because you have to familiarize yourself with a lot of parameters, and the only way to do that is to practice. So in assignment number 1 and assignment number 2, I've assigned you a lot of problems, but with the passage of time, I'm cutting down on the number of problems in the assignments. Like in Schottky diodes, the number of assignments would be even smaller, and then in photodetectors we will have even smaller number of problems in the assignment, and then I'm going to continue the pattern. But initially, the purpose of assigning you more number of problems is for you to practice, so that you can familiarize yourself with the terminologies and a lot of semiconductor parameters for this course. So that pretty much concludes the lecture. Do you have any queries?
No, sir.
All right, nice. Okay, so that would be it from my side. Take care, and Uzma, can you please coordinate with Naima as well about the in-person Silva Kuti Get session next week?
Yes, sir, I will, and inshallah, I will inform you.
All right, that sounds good. Okay, take care, and Allah Hafiz. And you have to submit this assignment by next lecture, okay?
Okay, sir.
And let Naima know as well that she has to submit the assignment number 1 today.
Okay, sir.
All right, take care, and Allah Hafiz.
Allah Hafiz, sir.